Hello everyone, welcome to Clean Coder channel. So today we are going to solve the problem number 94, binary tree in order traversal. So let's go through the problem statement quickly. So we are given the root of a binary tree. We are supposed to return the in order traversal of its nodes values. So this is the sample tree. So before doing this, let's understand what is in order traversal. So in order traversal of a binary tree is recursively defined as visiting left child, then visiting root, and then visiting right child. This we are supposed to do recursively. So if we dry run on this binary tree, so the output would be, according to this, would be left is not available, so it will output root 1. So for now it will go to the right subtree. So for 2, left exists, so first it will output 3 and then 2, so the output is 1 3 2, and this is the output. So let's read the constraints quickly. So the number of nodes in the tree ranges from 0 to 100, fine, and nodes value is given between -100 to +100, and a follow-up question is also given. Recursive solution is trivial, could you do it iteratively? Yeah, like this is a really good comment which they have mentioned. Everybody can do a recursive in order traversal, but for iterative version you need to think a little bit to write the code. So let's move to our whiteboard to discuss the various solution approaches. So briefly, there are two approaches to solve this problem. First one is recursive, second one is iterative. So recursive code is quite straightforward, I would say. We have a function in order, and this is our base condition. This is our base condition, and this is our recursive call to left subtree. This is our print statement. This is recursive call to right subtree. So this is the code, and it will do in order traversal, which is fine. Now let's see how we can do this iteratively. So in the interest of time, I have pasted my code snippet, which I have already executed in lead code problem editor. So let's understand this code and let's try run this example on this sample tree to get a better hang of how this algorithm runs. Frankly speaking, writing this in first go is a little challenging, and you need to figure this out by iterating on multiple test cases, but eventually you will end up doing something similar to this. So it's always better to have a correct solution handy. So let's go through this problem test case quickly. So the output is expecting a list, so we are making a list which will return in the end of the algorithm. So there is the stack in which we'll put the node in the algorithm. So now let's see, our current pointer is pointing to root, so current pointer is pointing here. Okay, now let's start our algorithm. Current is not null, and stack is also not empty, so we'll go to the inner while loop. So it says current is not null, stack dot add current. So I'll add 1 to stack and move to left. Okay, I'll move to 2. Now again, current is not null, so I'll add 2 also in stack and move to left child, which is 4. Okay, so again current is not null, and I'll add 4 to the stack and move to the left node. So now the left node would be null, and my current would be pointing to null. So I'll come out of this while loop. So after exiting this while loop, I'll do current is stack.pop. So I'll pop the topmost element from the stack. Okay, so my current will be pointing to 4 now. Cool, my current is pointing to 4, and at this moment I need to output this. So 4 is going to be in my result. Okay, so now I'll move my current to right of the present node. So right is again null, so current would become null. Current is null now, but in the next iteration of while, current is null but stack is not empty, so we'll enter this while loop. So since current is null, this won't execute. So now we are at this statement. So current is stack.pop, so we'll pop 2 and current will point to 2. Okay, so current is pointing to 2, and we'll add 2 to the output list, and we'll move the current to right. So current will be pointing to 5. Okay, so we'll move to the next iteration of this while loop. So now current is not null, we'll enter the inner while loop. Current is not null, we'll enter this inner while loop. Stack.add current, we are going to add 5 to our stack, and we'll move to its left pointer. Okay, so my current is pointing here. At this moment I'll exit the inner while loop. Now what would happen is it will pop the top element from the stack and point towards that. So now my current would be pointing to 5, and I'll output this in my output buffer as well, and I'll move to the right child of 5. The right child of 5 is null, so current would be pointing to null now, and I'll enter the next iteration of the while loop. Now current is null but stack is not empty, so we'll enter the while loop. Now current is null, so this while loop won't execute. Now we'll enter here. So current is stack.pop. At this moment we'll pop the stack, and current would be pointing to 1. Okay, current would be pointing here. Okay, so current would be pointing here. Let me erase these nulls. So I need to output this in my answer 1, and I need to move towards the right. Okay, so I'll move to the next iteration now. So while current is not null, this is sufficient to enter the while loop. Now current is not null, it will enter the inner while loop. Stack.add current, so now it will enter 3, and it will move to left. Okay, it will move to 6. Okay, so it will add that to stack also and move towards its left. Now it will point to null and come out of this while loop. So once it's out of this while loop, what it'll do is it will pop the top element from the stack. So current would be pointing to 6 now. and it will output that to the output buffer 6. Okay, and now current would move to right, so its right child is also null, so current would point to null now. Okay, I need to remove this 6. I should have removed it in the previous step. Sorry for this. So now this is the state of our algorithm. So now what would happen is, in the next iteration, our current is null, but again stack is not null. So this inner while loop won't execute. So I'll come to this current is stack.pop. So let me pop the stack. Now my current would be pointing to 3. Okay, so 3 would come in the output buffer. It will move towards right now. Current is current dot right. So now current would point to 7. So this is my present state now. So again, in the next iteration, current is not null, it will enter, and current is not null, it will again enter. So stack dot add current, it will put 7 in stack, and it will point to the left child of 7, which is null. So it will come out of the while loop. It will be something like this. Current will be pointing to this. So current is stack.pop, current would be 7 again. So let me do that again. Current is at 7. Now I'll add 7 to the output buffer, and current is current dot right. So current at this position is pointing to null, and one more thing, stack would also be empty since I popped 7 from the stack. So now current is pointing to null and stack is empty, so this algorithm would terminate, and I'll return this list, and this is my answer. This is my answer in order traversal, and it is matching. These two are matching, so my answer is correct. Let's see the space and time complexity now of this algorithm. So let's first compare the recursive version. For recursive version, time complexity is O of n, since I am visiting each node exactly once. Space complexity would be O of log n. This is because of the function stack, which would be proportional to the height of the binary tree. So this is the space and time complexity in case of recursion, and in case of iteration, the space and time complexity would be similar actually. So time complexity would be O of n only, because it is visiting each node exactly once, and space complexity would be log of n, because at any moment only nodes proportional to the height of the tree are present in the stack. So this was all I wanted to talk about this problem. If you liked my explanation, please like this video, and please subscribe to this channel if you want to watch similar videos. Once again, thanks a lot for watching.